Hi guys, today we're going to talk some more about graphs of rational functions and finding key features on our calculator. So we are going to be on page 32 in your notes, and we're going to need our TI inspired calculators for today. So for our first example, I'm going to go ahead and graph this function, which I've done already in my calculator. So I'm going to pull up that calculator screen. Here's my function, here's my graph. I can see I have an asymptote right here, vertical asymptote. I can also see a horizontal asymptote splitting my graph this way. So I can see a couple key features already. I can see I've got an x-intercept over here. So we're going to look at all of those things that we've talked about with graphs before, as well as things like minimums and maximums, end behavior, increasing and decreasing intervals, domain and range, everything that we could be concerned with for a graph. So the first thing I'm going to do is draw a little sketch of my graph. So I'm going to leave the calculator up here, but just do a quick sketch on my paper. So I'm going to put my axes in, and then I know I've got sort of a scoop on either side of the y-axis. Okay, doesn't have to be perfect, just sort of a vaguely resembling sketch of what's on our calculator. So let's start using our calculator to find some of these key features. So the first thing listed on my paper is an x-intercept. And I know I have an x-intercept over here. So remember, on our calculators, we never have to guess. We can just use our calculator to find that exact spot for us. So menu, analyze graph, and 0. That would be right here. There's my x-intercept, negative 2.33. The next thing on this list on my notes paper is the y-intercept. So I'm going to go ahead and pull up the table to try to find the y-intercept. And the y-intercept happens when x is 0. So I'm going to hop up to when x is 0. And I can see my y value is undefined. So let's take a look at our function here. Undefined means that 0 is an x value that I can't actually plug into my function. Otherwise, my function is undefined. So if I take a look at my function, I have 0 on the, or I have x, I should say, on the bottom of a fraction here. If x is equal to 0, this is undefined, and so my function is undefined. So that means that I have no y-intercept. But I do have a vertical asymptote when x equals 0. And we could see that from our function. We did this a few lessons prior. I can see that since x is not a reducible factor, that means it's going to be an asymptote. So I have a vertical asymptote at x equals 0. And then if I hop back to my graph really quickly, I can see, let's put our table away here. I can see that I do have right at the y-axis this sort of line where my graph splits. So I'm going down this way, and then all of a sudden here I come from up above. So I have a vertical asymptote at x equals 0. So I'm going to go ahead and just kind of get a different color, sketch in that asymptote that we have. And then I can also see this split horizontally. I've got a horizontal asymptote as well. And we can actually figure out roughly where that asymptote should be using our calculator. So if I go to my table again, and I look at the y values that I've got here, and I see I'm in the 2s, and my decimals for 2s are getting really small. So what I'm looking at is as I go farther and farther this way, what's my y value getting really close to? So we're at 2.75, 2.78, 2.8. So I'm way out at negative 52 right now, and we're still at 2.8. That tells me that this is getting, the y value for this portion of my graph is getting really, really close to 3. Now I could take this the other way as well, scrolling, scrolling, scrolling. And now I'm looking at really big values. So values this way on my graph. So at 20, we're at 3.3 repeating, and we're going down this time, 3.31, 3.30. And we're just above 3.17, 3.14. So we're up at positive 50. And oh, there's pi 3.14 approximately. We can see that we're getting really close to 3, but this is from the other direction. That should make sense. So for this portion of my graph, we were rising very gradually towards 3. For this portion of my graph, I was descending really gradually towards 3. So from either end, we're approaching 3 for our y value. So that tells me our horizontal asymptote should be at 3. That's important when we talk about end behavior. So we talked about end behavior for our polynomials. And we only looked at for the polynomial I have, is my end going up or down? If it was going up, we said y was approaching infinity. If it was going down, we said y was approaching negative infinity. Those were the only scenarios we had to worry about for polynomials, but for other types of functions, y doesn't have to just go up or down, right? Y isn't necessarily going to go up forever or down forever. As we're seeing with our rationals graph, we're coming out this way and just gradually getting closer and closer to 3, this horizontal asymptote. And then this way again, we're just gradually getting closer and closer to 3. So on the left end of our graph, right, when x is a negative number, we're getting really close to 3. So I'm going to say y is approaching 3. And then on the right end of our graph, where x is a positive number, again, we're getting really close to 3. So again, I would say y is approaching 3. So something a little different with our end behavior here. And then for our domain, remember those are x values that it's okay to plug in. Our domain for our rational functions is going to have to take into account any vertical asymptotes or holes, right? Any of those excluded values for our function. So we know x cannot be 0. So that means we can have anything from negative infinity up to 0, or anything from 0 up to infinity. We just can't have 0 itself. That's why I had to split this up into 2 sort of intervals here with parentheses on the 0, because I can't actually have 0 as a value. What I'm essentially saying is I can have all real numbers except x cannot equal 0. That's what I've said here with my interval notation. Now let's talk about minimums and maximums. So let's go back to our graph here. And I'm going to go ahead and zoom out just a little bit. So menu, zoom, let's zoom out a few times. Okay, so I can see that I'm, just as we talked about, just very gradually getting close to 3 from this end. So as I read my graph from left to right, I'm coming down, 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 and then really abruptly down. And then I pick up here from however high up, and I come down really steeply and then gradually down, down, down. We don't have any mountaintops. We don't have any valleys. So as we're asking about minimums and maximums, we have none on our graph at all. Remember, just as a reminder, local minimums and maximums are points that are the highest point or the lowest point for that area, but not the highest or lowest point on the entire graph. So a hill, but you have a bigger mountain, or something like here, where my graph actually goes up forever, but I do have a hill here. This would be a local maximum. This guy right here would be a local minimum. It's a valley, but it's not the lowest spot on my entire graph. Global minimums and maximums would be the absolute highest point on the graph or the absolute lowest point on my graph. Now let's talk about increasing and decreasing intervals and negative and positive intervals. So remember, when I am increasing, that means as I read my graph left to right, my y values are going up, okay? So that means I've got some sort of trajectory like this on my graph. It can be very, very gradual. It can be really, really steep, okay? But increasing means as I read from left to right, I'm going up. My y values are increasing. We don't have any place on our graph where our y values increase as we go from left to right. As I start on the left end of my graph, I'm very gradually decreasing and then sharply decreasing. And then I'm very sharply decreasing and then gradually decreasing. So we're decreasing the entire time here. So that's why we only have decreasing listed on our notes. So we're decreasing everywhere except I have to remember that excluded value. Some of the intervals that look really similar to our domain here, because at 0, we don't have a point on our graph, right? We have that vertical asymptote, so I'm not increasing or decreasing there. But everywhere else, we are decreasing. And now let's talk about positive and negative intervals. So as I look at a graph to determine positive and negative intervals are places where my graph is above the x-axis, where my y value is positive. A negative interval is a place below the x-axis where my y value would be negative. So I'm going to zoom back in here. So we can take a little bit, maybe nicer look at where I've got a negative interval. Okay, so this chunk is, this piece here is never going to dip lower than 3 on my y-axis. So I know nothing negative from there. I see right here where I have that x-intercept is where I've switched from having my graph above the x-axis to now having it below. So I've got a negative interval that starts when x is negative 2.33. That's the spot at which I switch what side of the x-axis I'm on. And then this continues until we hit our x value of 0. Remember, 0 is that asymptote. So I can't actually have an x value of 0, but immediately sort of before 0, we're negative, right? We're below the x-axis. And then immediately after, we're in this chunk up here, so we're above. So our negative interval is going to be from negative 2.33 until 0. So negative interval from negative 2.33 until 0. Anything else I would describe would be a positive interval. And then our range here. Remember, range are those y values. What values for y could I possibly get out of my function? So we know that we don't have a y-intercept, right? Because of that asymptote, and that impacted our domain, our vertical asymptote. So the other thing that we know is that because we have a horizontal asymptote, that's going to impact our range. So we know that we never actually will get to a y value of 3. So our range is going to be everything but 3. Just like for our domain, that was everything but 0. So since y cannot be 3, we're going to write some intervals that give us every other possible y value and exclude 3, since we have that horizontal asymptote there. So our y value can be anything from negative infinity up to 3, and then anything beyond 3, so 3 to positive infinity. Again, since we have that horizontal asymptote, when y is 3, that means I can't actually have 3 as a y value, but anything else would be fine. We're going to take a look at this first your turn example. So example 2, we're going to take a look at really quickly. We're going to do a quick refresher on increasing, decreasing, and positive, negative intervals. I know we just looked at negative and decreasing. So we're going to take a look at if I've got a positive or negative interval. So here's this next function graph for us. This time we're in sort of 3 chunks. So as I'm looking at increasing versus decreasing, that means, again, I'm reading my graph from left to right. So this first piece over here, increasing as I read from left to right. So I need to know, where is this asymptote? So I'm going to go back to my function, and I'm going to factor the bottom of this. So x squared minus 4 is the difference of squares. That would give me x plus 2 times x minus 2. And I would expect asymptotes at x equals negative 2 and x equals positive 2. Now I can check that on my graphing calculator. So if I pull up my table, at positive 2, undefined, because we have an asymptote, and at negative 2, undefined, because we have an asymptote. So that means that I have an increasing interval, so my graph is going up, from negative infinity until x is negative 2. So I'm increasing from negative infinity until negative 2. And then if I look at the next portion of my graph, we're increasing again. This looks like I have an x-intercept at the origin, but since I'm on my calculator, I'm going to double check. So menu, analyze graph, find that 0, find that x-intercept. I could have also found the maximum here, right? The sort of top of my hill would have been another way to go. Analyze graph, maximum, because that's where I would switch from increasing to decreasing. Again, 0, 0 there. So from when x is negative 2 then until x is 0, I have another increasing interval. So just to take a look at that on my notes, from negative infinity to -2 for that sort of leftmost portion of my graph, and then from -2 to 0. Now, let's take a look at our decreasing portions. So after I sort of turn the corner, I'm decreasing. So I have a decreasing interval from when x is 0 until my asymptote here, which we know happens at +2. And then I'm on this last portion of my graph. So here's where x is +2. So from when x is +2, as I read my graph from left to right, we're again going down. So from +2 until infinity, we're decreasing. Just take a look at my notes really quickly. From 0 to 2 for the sort of middle chunk of my graph right here. And then for that last portion, all decreasing. And now let's talk about positive and negative. So these two pieces of my graph are above the x-axis, right? Above the x-axis. Since we've got a horizontal asymptote here, they're never going to dip below. So these two portions are positive. So I'll describe those in just a minute. If I look at this sort of middle section of my graph, it's below the x-axis, then I touch the x-axis, and then we're below the x-axis again. That spot where I touch the x-axis at the origin at 0, 0, I can't count as negative because it's not. Negative means below the x-axis. Since it's on the x-axis, it's not negative. So my negative piece would be from when x is -2, right, at that asymptote, until 0. And then from 0 until our other asymptote at +2. Our positive sections of our graph, our positive intervals, would be from when x is -infinity until that asymptote at -2. And then this other section here from that asymptote at +2 until forever, until positive infinity. I want you to go ahead and pause your video and try example 3. I'm going to go ahead and move on to one final example to look at together on page 33, example 4. So this time our rational function is modeling something, right? That's why we care about these things, because we can use them to represent real life scenarios or problems. So our problem here says from 1985 to 1995, the average daily cost per patient in dollars at community hospitals in the United States can be modeled by this function, where x is the number of years since 1985. Graph the model, and then we'll answer a couple of questions. So I went ahead and graphed this on my calculator. I did have to adjust my zoom here. When I first hit enter, I saw nothing on my screen, so I did zoom it, and then I zoomed out just once to get a nicer picture. So notice that my scale on my y's is going by 100s, okay? So this is way up there. Now, my first question is, what year did cost peak? Well, peak tells me I'm looking for a maximum. So I want to find this maximum here. So menu, analyze graph, maximum. Okay. Now, year is an x value. So I'm going to jot down this point really quickly, 9.57, 853. And then I'm going to put my graph away for just a second. And again, it says, what year did cost peak? And then it says x is the number of years. So I know I want my x value here. But it's asking me what year, not after how many years. So x is the number of years since 1985. So I need to take 1985 and add on that x value. Now, my x value is a decimal here, 9.57. So this would give me 1994.57. So you could interpret that as mid-1994, July-ish of 1994. That's what year the cost peaked. B, how would you use this model to predict, or would you use this model to predict patient costs in 2005? Explain. So 2005 would be, let's see, 20 years after the start of our model. And notice our model says it's for these specific years. So I want to say no right out of the gate because the model is for a 10-year period. Okay, it specifies that 10-year period. But let's go ahead and look at our graph. Sometimes models are okay immediately before or immediately after. But let's go ahead and do a quick trace for when X is 20. So I'm just going to type in 20 here and have it jump. So when X is 20, right, in 2005, it's telling me my patient costs are $24.80. Does that seem reasonable? Like, and if I were to pick a later X value, let's say X is 30, that would be down here. My patient costs, my daily cost per patient would be negative. That also doesn't seem reasonable. So no for a couple of reasons. No, because the model is for 1985 to 1995. And then also 2005 is too far removed from that model that the values we get for that cost don't seem reasonable. Cost values or Y values don't seem reasonable for 2005. Okay. There is one more example for you to try. So you hopefully paused your video and tried example 3. If not, go ahead and try example 3 now and also try example 5. Okay? And that's the end of our notes for today.